Hello there, my pre-calc students. This is Dr. John Schrage, and I am here today thanking you for being great students with the substitute today and making some progress forward in the book. We're going to call this 1.4. In fact, I checked in your new textbook. It's a later section. I want to say 1.6, maybe 1.7, something like that. I'll get them renumbered at some point. Anyway, today we're going to be learning about a topic called transformations of functions. And what this means, again, you saw it in Algebra 2, just maybe in a slightly different way. What this means is how we take basic building block functions that we're going to call the parent functions, and we can turn them into looking like anything. Any way we want the function to be stretched and compressed and slid around and moved around on the graph paper. So any function is built out of pieces called parent functions. And there's a list of the parent functions and example graphs of them on page 64, I believe it is, in your new book. And I recommend you have that out when you are working on the assignment here. Let me just give you a little tour using Desmos here of the parent functions. This is actually a term that the author of your textbook likes a lot. It's going to keep coming up all the way till May as we learn about trig parent functions and log parent functions and all this kind of stuff. The most basic parent function is just a line, the linear parent function, which is the one I'm showing you here right now, where just f of x is equal to x. It's just a basic line, and any line that you would make as a graph could be made out of this line. We might have to shift it vertically or horizontally. We might have to tilt it or stretch it or compress it or dilate it into being smaller. But as you'll see in a little bit, any line is just related to this basic line, f of x equals x. It's a less common function to work with except at the beginning of pre-calc, but another nice function is the absolute value function. Now, the graph of it's this weird V-shaped thing, but lots of graphs come from this V-shaped thing. We might have to take that V-shaped thing and move it up and down or left and right or flip it over or something like that. By the way, in Desmos, you might not know how to make the absolute value function. When you're typing in your function, the most efficient way to get absolute value is with the pipe symbol, which is right above enter on my key. It's the shift above the backslash right there. It's the straight up and down line that kind of looks like the absolute value symbol. And so you could type, absolute value of x like this and you'll get it. If you can't find the pipe or for some reason on your keyboard it's mapped differently or something like that, another thing that always works is just ABS. ABS of x is the absolute value function. I'll switch it back to the absolute value symbols using the pipes. Another basic parent function is square root. The square root of x makes this sort of curve-shaped function that extends out to infinity in the positive x direction and actually out towards infinity in the y direction, although very slow, and then does not extend past 0 in either direction here. Again, there'll be all kinds of functions that we can get by stretching and shifting and compressing and flipping this graph, but it is what it is. It's the graph of f. Now, you might not know how to make a square root symbol in Desmos. It is SQRT. SQRT, and then you can type whatever you want inside of there. I think there are menus down here at the bottom that you can dig around in on Desmos to get it where you have a toolbar or something like that would help you too. Another very important parent function is the quadratic function, or x squared. You've been working with quadratic stuff since like 8th grade math or 7th grade math or something like that. That may or may not have ever used the word parent function. To be honest, I had never heard the term parent function until I started teaching the class with this book by Larson. I don't know that that's a common term. But the idea that there's this basic building block of a parabola. Now, other graphs will be maybe shifted or stretched or flipped, but they will be in some sense transformed, but they will all those kind of parabola-shaped things will be based on this basic parent function. Your book throws in, while it's at it, the cubic function, x cubed. Same sort of game. It's just a parent function. We'll be able to identify it. We'll be able to flip it or rotate it or stretch it or whatever. And 1 over x will be our sixth and last of the parent functions at this time. There are a lot of parent functions. In fact, I think in the back of your book, maybe there's a set of them all plotted for you. In the old book, there was a graph back there. Maybe this book doesn't have it. But here's 1 over x. And that is again, certain graphs will be this shifted or whatever. If you don't know how to get a fraction like 1 over x in Desmos, let me just show you real quick here. When you're making a fraction in Desmos, always start with the bar. And the bar is the slash on your screen here, like down by the question mark and so on there. When you have the slash in there, then you can type what's on the top, and you can click over here and type what's on the bottom. Okay, so here's a whole mess of parent functions, and we are going to be able to do things with them today and recognize them and plot them and transform them and so on. Now, I'm actually going to take a moment here to introduce one more parent function to you, because this parent function, even though it's not in the list right now of what you're doing, illustrates the transformations more easily than other parent functions do. And that is sine. Now, you don't necessarily know what sine, like sine of x, is. It comes from trig. We're going to do it to death in like February, March, and April. But right now, can we look at this graph and just acknowledge it's clearly some kind of function? It passes a vertical line test. It has a domain, and it has a range. I mean, it is a parent function. We're going to be able to do things like transform it and so on. As it happens, sine illustrates the transformations maybe a little easier to teach than the other ones do. A lot of the other transformations are a little hard to see on some of the other ones. We'll see that in just a minute here. So right now, here in blue, I have some kind of parent function. It happens to be the sine of x. You don't have to know what sine is. Can we trust ourselves? It's a function. It does something. And we're going to find ways to transform it, to change it. And in order to do that, I have this rule that I have typed up here in Desmos that has an A, a B, a C, and a D in it. But right for this exact moment, that might be a lot as to what's going on right here. So let me go ahead and I'm going to make this, kind of teach these one at a time before I put them all in at the same time. The first thing I'm going to do is I'm going to make the same function, but I'm going to put an A in front of it. A times the sine of x. Now in Desmos, if it doesn't know what this letter A is, it's going to ask you, oh, is that a variable? In fact, why don't I go ahead and I'll erase these right here and I'll show you. It's asking, hey, do you want to add a slider for A? So if I put a slider in here for A is currently equal to 1, but I can slide back and forth and change the values of A. So right now, this function f of x is 3.7 times the sine of x. I'm going to change it to a color. If I long press on the button here that shows that it's in purple, I can get different colors. I'm going to make it red instead, maybe thicker. Let's see here. I'm just going to make this thicker and bigger just so it shows up on the projector better. All right. As I change the value of A, you can see I'm doing something to the parent function. I'm making something new. The parent function's still there in blue. But as I multiply the parent function by a number, I am stretching it out vertically. So by multiplying the parent function by a number, I'm stretching it out. Well, I'm stretching it out if that A is bigger than 1. If I start getting smaller than 1, I'm actually compressing, or the word that the handout uses is dilating, this function, getting it flatter and closer to the 0 there. So I can dilate the function, or I can stretch it. And actually, if I multiply it, if the A is a negative number, we actually flip it. So I can flip the function by multiplying by numbers that are negative. Now this illustrates nicely on the parent function that is sine. You can see how this stretch is happening. It is a little more awkward on, I'm going to hide these two guys right now. Notice if I click on them, it hides them. I'm going to go do the same thing to, say, the parent function x squared. Let's show this one. Here's a nice parabola. If I made the same thing, but I have it a times x squared, it is a little harder to see how this guy, the red one, is a stretched version of b. But that's just part of the geometry of parabolas. It is a little hard to tell when they're stretched and compressed and stuff like that. That's why I like to teach it using sine. Sine, it's a little easier to see what's going on. So we still have this function here, this parent function sine, and I have multiplied it by a. But notice I've multiplied it in a very particular place. I multiplied outside of the function. If it would help, maybe I could put some parentheses here just so you can see what's going on. Here's the inside of the function. Here's the outside of the function. I multiplied on the outside, and multiplying on the outside was a vertical stretch or a vertical compress or a flip, a vertical flip. Now I'm going to show you another one. I'm going to take that a out of there, and I'm going to put a b inside of the function. Now, right now, because I don't have a b, it's saying, hey, you want to add a slider for b? Sure, I'll put a slider here for b. Now, when I drag b to different values here, so now like b is equal to 2.4, notice what's happening to my function. The parent function's still there in blue, but now the red shows the transformed function. And you see how it's compressing in from the sides. It's compressing horizontally. As we multiply, we compress horizontally. Well, we compress horizontally as long as the number b is greater than 1. If we start getting smaller than 1, you see we're actually stretching, stretching horizontally. And in fact, if I go all the way to negative, we actually flipped it too. So multiplying here made it horizontally stretch, or horizontally dilate, or horizontally flip. Now notice how this is different though. This b is inside of the parent function. By operating on the inside of the parent function, instead of being a vertical stretch or a vertical dilation, it's a horizontal stretch or horizontal dilation. And again, I could illustrate that with any of these parent functions. Let me turn these guys off, and let's switch over here. How about square root? There we got the square root's parent function. And if I add another guy over here, it'll be the square root of b times x. Okay, these guys are too close in color, so I'm going to choose a different color here. How about red and fat line here? By choosing different values of b, I'm pushing it closer to the x-axis. I'm compressing it. Or by getting to smaller values, I am stretching it out. And going to negative, I flip it over the y-axis. Now I get it. That's a little hard to see. How is the red curve the green curve, but compressed? Well, yeah. Let's wait till we get more experience with that and I'm in the room to show better examples of that. All right. You'll be able to get a start on the homework this time. All right. Let's do another thing that we could do this function. Suppose I took my parent function sine of x, and instead, after I did the sine of x, I added a constant. Now, right now, because I don't have that c, actually, let's call that d. Let's call that d. After I add that, I'm going to have to put that on there. Look what happens. All I do is I take the sine of x, and then I'm adding some constant. And all that does is shift the function up, or if the d is negative, it shifts it down. Adding or subtracting a value here shifts the function vertically. If it's done after or outside of the function itself. Here's my parent function. If I add a number d afterward, it either shifts it up or should shift down. Now this is easier to see for some of these other guys we got over here. Let's do the same thing here with our old parent function about the square root of x. Now as I change the value of d, I've taken square root of x, and then outside of that I add d, where here d is 1.3 or whatever. See how it's vertically shifting the function? And this works because I added the d after or outside of where I did the parent function. Finally, there's going to be the letter c. If I added, let's go back to this parent function of sine. If I add some constant c inside of the parent function, I'll have to add a new slider for c. Look what happens as I change the values of c. It shifts left and right. It shifts horizontally. Now, it's probably shifting in a direction that you are surprised by. Sorry here. Notice as I make c bigger, it's shifting to the left, and as I make c smaller, it shifts to the right. It's because, actually, to be more correct, we should be using minus c here to do it like what's doing in the book. Now, as I shift to the right, this function goes to the right. If I make c negative, it shifts to the left. Sorry. Okay, there we go. And again, this is actually not so hard to see on some of these other parent functions. Let's go back over here to square root. If inside of the parent function I subtract c, now, see how it's taking the function. If I make c positive, we're shifting to the right. If I make c negative, we're shifting to the left. It's a horizontal shift. There's a handout for you on Google Classroom that explains what all these guys are doing and so on. You should have access to that. That'll be no problem for you. It'll help you with that. The amazing thing about this is we can do all of these things at the same time. I'm going to go ahead and turn off this one for square root of x and go back to sine. Where did sine go? Here's sine. Why don't we make it a times the sine of bx minus c plus d. Well, now we can do all of the transformations. We could shift it. Where did my function go? There's the parent function. If I put these guys at their original positions here, 0-ish and 0 for the offsets, and 1 and, where'd that go? 1 and 1 for the A and the, where did the A go? There he is. There you go. All right. Get that out of here. All right. Now I have A, B, C, and D as these sliders. Let me put them in order. That'll make it easier. Okay. A is the vertical stretch. As I change the value of A, I am vertically stretching and maybe flipping and dilating. B is the horizontal stretch. C is the horizontal shift. And D is the vertical shift. So I'm going to put another function in here just to show you. Let's say I was anticipating f of x equals, let's just say 2, and I'm going to turn the function off so we can't see it just yet, 2 times the sine of 3x minus 1 plus 2. Oops, I don't have plus. Plus 2. Now, before I even turn this graph on so we can see it, notice what's happening here. I can see that I have started with a parent function of sine, but I have vertically stretched it by 2, so it'll be taller. I have horizontally compressed it by 3, so it'll be squishier towards the y-axis. I have shifted it horizontally by 1 and vertically by 2. So it'll be off to the side a little bit and up a little bit. And if I turn this on, you can see that's exactly what we got. It is vertically stretched. Let me turn this red one here off. Our new function Here, let's see if I can make this guy a better color. How about black? The black function, with dotted lines right there, is stretched vertically. It's compressed horizontally. Right? It's stretched vertically, compressed horizontally. It's shifted horizontally, which is a little bit hard to see, and it's been pushed up by 2 units. This idea of how we can transform functions in this way is a hugely powerful tool. It helps us anticipate what graphs will look like just based on what the equation looks like. I did it over here for sine, but we could do the same sort of thing over here for, let's just say, excuse me, square root. Let's put square root back up on here and take the sine back off. Again, I'll turn this guy off for a second here. Let's say we had negative 2 times the square root of x plus 1. What are we anticipating this thing to look like? Okay, we're multiplying by negative 2 outside of the parent function. So we think the parent function has been stretched, but also flipped. So I'm thinking that my function will look like the green curve, but it'll have been stretched vertically and then flipped over. And then plus 1, that's addition outside of the original function. And so it'll all be shifted up a little bit too. And if I turn the graph on, it's a little hard to see what's going on here, but you can see I've stretched the function, flipped it, and shifted it up. Now this is a little trickier to see how this works for things like some of these other parent functions. If I did x cubed, here's the parent function for x cubed. Now let's transform that guy. How about f of x equals negative, but instead of x cubed, how about x minus 1 cubed plus, how about minus 3? Okay, what happened here? I have multiplied by negative 1 outside of the parent function. The parent function is whatever cubed. The green function here shows I have flipped it. The negative 1 shows I've shifted it horizontally. And the negative 3 shows I shifted it vertically and it shifted down. If I just grab another one here real quick, here is 1 over x. If I wanted to make one like this, f of x equals, all right, the parent function is 1 over whatever. What if instead of 1 over whatever, it was 5x minus 1? Minus 7. There we go. So what has happened here? The parent function is 1 over x, but we have transformed that by saying 1 over, inside the parent function, I multiply by 5, which should be squishing it closer to the x-axis. If I took out that minus 7, you'd be able to see how the blue curve is pushed closer to the y-axis. It has been compressed horizontally. And minus 7 means shifted horizontally. I know these guys are a little bit tricky. I am providing you also with a second explanation that I found online. A guy who goes over this very carefully and does a great job. Some people will be ready to just race into the assignment. Some people probably will want to watch that second video, which is about 20 minutes long. Do what you need to do. Reach out to me if you have any questions with this. Again, you did this in like Algebra 2, but I get it. It's been a while. Maybe they use slightly different terms or they didn't use Desmos to illustrate it. Do what you need to do and reach out to me if you have any questions. And I appreciate your time and the fact that you're being great for the sub. Thanks.